In this video, we are going to do a brief introduction to integration using U-substitutions. So the first thing I'd really like to discuss, for reasons that'll become clear a little later on in some of the videos, is why are we doing U-substitutions? And in order to discuss why we're doing them, I'd like to give an analogy. So as I've made clear to everyone before, I am not great at remembering area formulas for lots of different geometric shapes. And the reason for that is that I prefer to know the area formulas for a handful of different basic shapes, like rectangles, triangles, and circles. And then when it comes time to determine the area formula for some other type of shape, my go-to method is to translate that shape into something that I know and figure out what the area formula would be from there, as opposed to just memorizing area formulas. So you can see how that might work. If you imagine that I have the parallelogram over here on the left, it turns out that the area of this parallelogram is given by its base times its height. However, it's much easier for me to see why that formula holds when I translate the parallelogram into a rectangle by taking this triangle right here and moving it until it's over here. Yes, the shape has changed, but the area, the only thing I care about, has stayed the same. And in making a change to the parallelogram, converting it to a rectangle, I haven't affected the area, and I've turned it into something that's more easily recognizable to me. And that's an analogy for what's going on with U-substitutions, both indirectly and later on when we use definite integrals directly. So let's bring that analogy to fruition here. What I have shown right here are what I believe to be my basic functions that we use very frequently in a calculus course. Over here on the right-hand side are the derivatives of those functions, and we've gone through a process of matching each function on the left with its derivative on the right. Because taking derivatives and finding antiderivatives are opposite functions, that's the second half of the fundamental theorem of calculus, the absolute easiest way to find antiderivatives is to recognize one of these functions over here on the right as the integrand, the thing being integrated, and to follow the line we have backward. So taking this top one as an example, the easiest way to calculate the antiderivative of the secant squared of u du is to find a common function, tangent of u, that has secant squared of u du as its derivative. So the easiest way to find antiderivatives is to be presented with something on the right-hand side of this table and to just follow the lines backward. However, we're not always that lucky. It's very rare, in fact, that we're just given one of those values and asked to find an antiderivative. For example, if I were asked to find an antiderivative of the function 2x e to the x squared dx, that's an example of a function that does not appear in the right-hand column of the table that was just shown. However, perhaps the reason that this function, 2x e to the x squared dx, does not appear in the table on the right is because the variable is wrong. So let's be a little more specific about that thinking. Let's imagine that there's a different variable called u, and there happens to be a relationship between the variable u of my imagination and the variable that I'm looking at currently, x, and that specific relationship is that u is equal to x squared. It follows from that relationship that the change to u is given by 2x dx, and then if I go back and take a look at my initial integral, where I'm being asked to find an antiderivative, if I shuffle around this function a little bit, in particular take the 2x and move it toward the end, then we can see a very specific pattern in this integral. This thing that we have written as x squared in the exponent, I could change out directly for the variable u. And this expression that we have over here highlighted in green, 2x dx, is precisely the right-hand side of this equality. So directly substituting x squared, the thing in blue, for the other half of this equality, and directly substituting 2x dx, the right-hand side of this equality, for the left-hand side, this antiderivative that I'm being asked to find is equal to a different antiderivative with a different variable. It's asking me to find the antiderivative of e to the u du with this new variable u. What's wonderful about that is that this thing, e to the u du, does appear in the right-hand side column of that large table we displayed for the variable u. And therefore finding its antiderivative is entirely straightforward. Its antiderivative is just e to the u plus some sort of constant c. At this point, the problem is entirely complete except for the fact that u was entirely a variable of our imagination and creation. The initial problem that we were given knew nothing of the variable u. And therefore, as a kindness to the person who asked us to compute this problem, we should translate back from the variable of our imagination to the variable that we were given. And the way that we do that is via the relationship between those two variables given right here. So instead of writing that u, we'll now go from the left-hand side to the right-hand side and plug x squared in for u, and the final answer to the entire problem is right here.